Welcome back to Computer Science 4300, Intro to Game Programming. Here we are at Lecture 3. So today we're going to be finishing off our sort of speed run of C++, if you will. We're going to be going over a bunch of different topics in C++. And if you don't get it all the first time through, that's okay. Just pause the video and, replay it and stuff like that. If you're watching live here on Twitch, then if there's something you don't understand, I'm not going to be rewinding live. You can just wait till the end and then watch the VOD later. So let's get into... first, the next class we'll be going over some C++ and SFML coding examples, and we'll be looking at assignment 1 as well. So on Tuesday, the next lecture, we'll be going over assignment 1. So let's look at the slides here, and we'll jump right into it. So today we're going to be doing some slides, and then some live programming, then some slides, and then some live programming back and forth. Okie doke, let me get my laser pointer. There we go. Excuse me. So lecture 3, some more C++ programming. Today we're going to be talking about memory-related things, mostly. So C++ memory, of course, as we talked about last time, one of the sort of pros/cons of C++, depending how you look at it, is that you have to manage your own memory, right? So what does that entail? Well, there's two different types of memory in C++. There's stack memory and there's heap memory. And if you're not familiar with stack or heap memory, well, we'll go through a sort of introduction to that now. So when a program is launched, the operating system gives it access to a number of areas in memory. So depending on the operating system, depending on the compiler, the program is going to be able to have access to some amount of memory on your system. The main two types of memory that we can manipulate, at least in C++ and in C, are the stack memory and the heap memory. So both stack memory and heap memory are stored in RAM. The main difference between them is determined by the OS when the program runs and the amount of time that it takes to, say, allocate memory on the stack versus the heap, and how we actually allocate that memory. So, stack and heap memory. At a basic level, they're both just memory. They can store the same data, right? So you're just storing bits in memory. However, so what we're going to do in the running of our program, we're going to request some amount of memory either from the stack or the heap, and it's going to let us use that memory if there's enough memory available. So the main differences between stack and heap memory is, first of all, it's the size. Oh, geez, that's the worst circle ever. The size of the available memory. Second is the way that the memory is found and allocated. So we have a different syntax for allocating stack versus heap memory, and also what goes on behind the scenes is also very different. The speed of memory allocation is also very different. So stack memory is way faster to allocate than heap memory is. The way that we request memory in our code is going to have a different syntax, and also memory and objects that live on the stack are going to be deallocated when it leaves scope, versus heap memory is not affected by the scope of the currently running program. So let's just look at some basic examples of this. So here we have a very basic main function, or whatever function. So if we just say something like int val equals 5, so we just declare a value as a type integer and we give it some value, then that memory is allocated on the stack. So by default, the natural way we would allocate a variable, it gets assigned to the stack, okay? And if we want to use the heap, then we have to invoke the new keyword. So if you're used to C, then in C you would use a call to malloc or memory alloc, but in C++ there's a shortcut to malloc, which is just the new keyword. So if you come from Java, for example, you're already familiar with the new keyword. However, when we allocate memory on the heap in C or C++, what we get as a return value to this new operator is a pointer to where that lives in memory. And we'll get into pointers, but just realize that int star means an integer pointer. Okay, so int value, that lives on the stack. Int pointer, heap value, equals new int, that lives on the heap. And if we wanted to assign a value to hval, like if we wanted to store an integer value inside that integer pointer, then we have to dereference that pointer. And we'll get into more of that syntax in a little bit. Similarly, if we want to allocate arrays of data in C++, we would say if we want a stack allocated array, we would say int a5, and then that's an array of integers of size 5. If we wanted a heap allocated array, we say int star heap array equals new int and then the size 5. And again, what we get back is a pointer to that data living on the stack. So what we will see is that a pointer is just a memory address. So if anyone ever asks you what's a pointer in C or C++, well, a pointer is just a variable that stores a memory address rather than a value. And then we can access either of these arrays via the standard square bracket operator that we're very familiar with already from other programming languages. The same thing goes for objects. So if I have an object of type myClass, I can allocate an object of type myClass on the stack by just saying myClass C and then passing into the brackets the arguments. And if you use this syntax, it's allocated locally on the stack. Or you can allocate with new, again, for a heap allocated object. So you can say myClass star, which means a pointer to myClass, and this would be HC for heap class equals new myClass and then the arguments. So the syntax is a little bit different with objects versus base data types, but it's not too difficult. The other difference here would be that, as I mentioned before, stack allocated variables, they get destructed or they get removed from memory when they are when the scope of whatever function that allocated them leaves scope. So this myClass C, as soon as we exit this function, now it's a main function, so the whole program is going to terminate, but pretend this is some other function, right? As soon as this curly brace is reached, then all of the variables here will be removed. However, because C is stack allocated, that variable, that object is going to be destructed. Now, I'll get into a very concrete example of this. So that was a little, if that was a little confusing, I'll show an example with like a fake stack and a fake heap and stuff. So stack memory has a predefined size based on your compiler and your operating system, but it's typically quite small. The majority of the things that live on the stack aren't large data. We can't use it to store large amounts of data. So it's very easy to run out of stack memory. Sometimes you may have seen Stack Overflow, so that website is very popular. But what a Stack Overflow is when you put too much stuff on the memory, or on the stack for whatever reason. So local variables without new called in front of them are allocated on the stack by default. Program function calls and return addresses are also allocated on the stack. So program function calls and return addresses. So this has to do, if you've ever programmed in assembly at all, you'd be very, very familiar with this and how the stack works. I recommend watching some tutorials on like the very, very basics of assembly, because you'll get very, very familiar with how the stack functions. A lot of those details about some of the hidden variables on the stack, which relate to like where to go next in memory and which function do I unroll to in my call stack, etc. They're all there, but they're all hidden from you, okay? So if you want to know more about that, you can, but it won't really be necessary for this course. So let's do an example here of some stack allocated memory. So what we're going to do, here we have our stack, okay, over on the right-hand side, and this stack is going to grow from the bottom up. Okay, so everything, just like a normal stack, you should all be familiar with the stack data structure. It's first in, last out, okay? So, or last in, first out, whichever way you want to say that. So the first thing that goes on the stack is going to go on the bottom, then something's going to go on the top, on top, on top, on top. All right, so here we have some code over here. We are going to say int I equals 6, int b equals 10, and then we're going to have a point, which is just some custom class that we've created, and that point is going to have an X and a Y. So just picture a Euclidean plane. We have some point data structure that has an X and a Y, and so that's going to store both of those things. So the first thing we're going to do is, as our program operates here, we are currently on the first line right here. So I've got this little red arrow indicating what is the current line of code that's being executed. So we've currently executed int I equals 6, and we can see here that on our stack is the value of 6. Now internally, this variable I is somehow pointing to where that variable lives on the stack. Okay, but we don't need to worry about that. Whenever you refer to I, it is magically pointing at this place in stack memory. Now, as I said before, there's probably a bunch of stuff down here relating to like the operating system and the running time of the program and where the function call pointer is to int main, but we don't have to worry about that for this course. We just worry about what happens after int main is called. Next, we're going to say int b equals 10. And that's going to push another value on the stack right here. So value 10 goes on the stack above value 6. Next, we are going to push a point p, and that has an X and a Y location. And the first value is going to get pushed onto the stack first, and the second value is going to get pushed onto the stack second. So what happens here is on the stack, these two values on the stack, that is where our point object lives. Okay? All right, so what happens when we exit main now? Well, we're going to exit the main function, and because it's a stack, these objects that we've allocated on the stack are going to be removed from the stack in reverse order that we allocated them. So the first thing that's going to happen is this point is going to be deallocated, and so we'll see that 4 and 5 get popped off the stack. Then B is going to be deallocated. So 10 gets popped off the stack, and then our 6 gets popped off the stack. So any variables that are allocated on the stack get removed in reverse order once the scope of whatever function allocated them has terminated. Okay? That's pretty intuitive. So the stack memory is also known as static memory. All stack memory allocation sizes need to be known at compile time. So the program needs to know if you are ever allocating any memory on the stack, it needs to be that the size of that memory needs to be known at compile time. So what that means is that if you need something that, let's say you need an array which is dependent on some variable for its size, you can't use a variable sized array on the stack. That would have to use the heap. So memory allocation which depends on runtime variables, so dynamically sized memory, must be heap allocated. All right, so that's very important. If we want to say store an array of a given size on the stack, that size needs to be known at compile time and not at runtime. Heap memory. So heap memory, first of all, there's much more heap memory available to you in your program than on the stack. For all intents and purposes, well, okay, it's a little bit different for 32-bit programs running on 64-bit operating systems and stuff like that. But however much RAM you have is how much heap memory you have available to you. So that's pretty much the rule there. And you're going to allocate heap memory with the new keyword. So the syntax for that is you're going to declare the type. So for example, int or my class or whatever. So type star variable name equals new type. Okay, and then if type is a class, you would also have brackets with the arguments for that going into the class. So the new keyword under the hood is going to do some magic stuff and call malloc, which is a C function underneath the hood. And what malloc does is malloc is short for memory allocate. And the operating system, depending on how your operating system works and how your compiler is set up, the operating system is going to go out and find a contiguous chunk of memory that is whatever size you need, and it's going to return a pointer to it. And this is very complex and expensive, believe it or not. And then you can access the memory via a pointer. So the new keyword is going to return this pointer right here, and then you're going to be able to access the data, the memory that you've allocated by using that pointer. And here's just a quick diagram for you. I know you can't read this, but it fits all on one slide. Up here, like this part of this diagram, this is the flowchart for the logic of malloc. So every time you use the new keyword in C++ and you allocate memory on the heap, this whole shenanigans has to happen, okay? So we're going to see toward the end of the course that what we're going to want to do is we're going to try as hard as we can to minimize the number of dynamic memory allocations wherever possible in C++. And then once memory is dynamically allocated, it has to be freed and stuff. And so it's really complex. And so we're going to try and not use that as much as possible. But for now, we are just going to be looking at that. Here you go. If you want to take a screenshot now, if you want this link, okay? 3, 2, 1, and I'm moving the camera back up. All the students have access to the slides, and my webcam won't be on the slides. That's why I'm covering stuff up without really caring much. So let's look at an example of how the stack and the heap and pointers are going to operate together, okay? So somewhere in our RAM, we have the stack, and somewhere in our RAM, we have the heap. So what I've done here is I've put fake memory addresses on the heap. Now, of course, stack memory also has a memory address, but very rarely are we actually going to want to have pointers to things on the stack, okay? So I've just left out the memory addresses here of things on the stack, but I'm showing you sample memory addresses of things on the heap. So here we have an address, OX1, and in reality this would be like 64 bits long or something like that. It wouldn't just be a 1 or a 2 or a 3. It would be a big complex number, but of course I don't want to have that on the slide. So this is memory address 1 on the heap. This is memory address 2, 3, 4, 5. And just for the sake of argument, this is going to be of whatever size of the data that we have here, just for an abstract demonstration. Someone asked in the chat, are both stack and heap memory contiguous in memory? So what contiguous in memory means is that it's a chunk of memory that's all together, okay? So like if I want an array to be, if I got an array or an object that had all 3 of these locations in memory, we would say that that thing is contiguous in memory. Since the heap is all the memory, you wouldn't refer to it as contiguous. It's just all the memory. But we would say that we want contiguous memory for something. Okay. So let's go through this example. The first thing we're going to do, just like before, is I'm going to set up an integer I equal to 6. And because there's no new keyword here, the 6 just gets put onto the stack. Okay? Next, we're going to have int j equals 10. So j gets put over here on the stack, right? Value 10. Now, here's where the heap starts to come into play. We're going to say pointer star, or point, I shouldn't have called this a point because it's a pointer to a point. But we have a data structure called point, or PT here, okay? And we're going to want to allocate that point on the heap. So what do? We're going to have a variable, a pointer to that variable, right? PT star P equals new point. So we're invoking the new keyword, and we're going to pass in 5 and 4. So what happens when we do that is that the new keyword, C++, goes out and it finds us the first available contiguous block of memory that can take 2 values. Okay, so if those are integers, then those are 4 bytes each. If those are doubles, then they're 8 bytes each, etc. So here, it found us this contiguous block of memory because there was nothing in the heap yet. And this contiguous block of memory here has the values 5 and the values 4. So the heap is growing down, the stack is growing up. But what we see over here on the stack is the pointer value. So the thing that's on the stack here is the address of the point that we just set up, okay? So you see that? So this is the address PT star. So it's a pointer to our point object. So the thing that lives on the stack is the address of that. So if we look, then if we want to do something to this point, well, we can use that pointer because OX1 comes over here and it points to this address in memory. So just like when you want to send a letter to someone's house, right? Their address that you write is sort of a pointer to their house, right? And the post office can deliver your letter to that pointer. All a pointer is a memory address and nothing more. It literally does nothing more than that. The only complex part of pointers is the syntax and getting all the memory management straight in your head. So now that that's done, we've got this OX1 on the stack. And now the next thing we're going to do is we're going to allocate an integer array on the stack. Okay, so this is an int array of size 2, and we're going to have values 3 and 4 in it. Now, because it's stack allocated, it's going to go on the stack right here. So here's the 3 and here's the 4. Okay, so we've allocated all of our memory, and now we get to the end of the main function, or whatever function we happen to be in, or whatever scope. And all of this memory is going to be removed in the reversed order from how it was allocated, okay? So the first thing that happens is the last thing, or the first thing that gets removed is the last thing that was created. So that was our integer array here. So that 4 and 3 are going to be removed from the stack. The next thing that's removed from the stack is the pointer p. That gets removed from the stack. The next thing that gets removed is j, and then the next thing that gets removed is I. Okay? And you can see here, something really bad happened. We have heap memory that's still allocated. So what we've done here is we have set up a pointer to some data on the heap, but we haven't explicitly told our program to remove that data from the heap. So this is where memory management starts to come in C++, and where things start to get a little bit complicated, is that whenever you are manually allocating heap memory and using pointers, you have to manually remove that memory. So the way that we would remove that memory from the heap is with the delete keyword, okay? Someone just asked, is heap memory remaining allocated after every execution ever practically useful? That's a good question. So any memory left in the heap at the end of your program is never useful, right? Because your program has terminated. However, there are some cases in which you would want to allocate memory in one function and then say return the pointer and use that memory in another function, okay? So it's not always the case that you would want memory to be cleaned up at the end of a block of scopes or a block of code's scope. However, usually that is the case, all right? So you'll see by the end of this lecture where you would want to have that happen and where you wouldn't want to have that happen. Good question. So the C++ memory layout is actually, I've simplified it here by just drawing a heap and drawing a stack. The whole point of me showing this, no pun intended, was that the stack stored this pointer and the heap stored the data. And the pointer was just the memory address of where the data lives. Okay, so it's actually quite complicated how the program memory is actually laid out. It is completely specific to the operating system and the compiler, and a lot of these details won't matter for this course, but I highly recommend at some point learning a bit of assembly language, because the hello world example in assembly will teach you a lot about this and how it works. So just for now, remember that the stack memory is fast but limited, and the heap memory is larger but slower, okay? And the stack grows down and the heap grows up, and so memory addresses are a little bit out of order, but that's not a huge deal. So we've talked about pointers a little bit. Let's go into a little bit more detail with pointers, because it's vital to know what pointers are for this course and for all C++ programming. Now, you can get away with not using pointers in modern C++. However, you need to know what pointers are in order to know why you can get away without using them. Oh, if you just give me 1 second, I have a visitor at the door here. Here we go. I got a helper today. This is Luna. She was crying at the door. I couldn't leave her crying, so I just thought I'd go get her for a minute. She just turned 2. She's very sweet. I think she wants to get into the garage because she really loves the garage. So let's just take a little bit of a lecture break to let her into the garage. So I'll be right back. All right. She is now playing in the garage. No, she doesn't know C++. All right, let's get back into the lecture. So C++ pointers are the same as pointers in C. They just point to a memory address, okay? A pointer is a variable that stores a memory address, and that is all. That's it. So modifying the pointer variable modifies the address that it points to. If you just say, for example, in our example here, if you modified the pointer p, it would not modify the heap data. It would just modify the address here that's on the stack. Okay? So, where was I? Yeah, to modify the value of the data in memory that our pointer points to, we have to dereference it. And I'll show an example of that. So raw pointers can be very unsafe because of this. And in modern C++, wherever possible, we would like to avoid using pointers unless you absolutely have to use pointers. So let's look at an example here. Now, one of the issues that many people have with C++ is the overloading of symbols. And what that means is there's going to be symbols that do multiple things, depending on the context of where they are. So this int I equals 6, that is a local integer variable that is stored on the stack. Int star p, that is a pointer to an integer. Actually, just let me walk through this. So I've got the stack here, and the stack is going to grow downward this time, I think, just to be a little bit more confusing. So int I equals 6. When I execute that line of code, now I've got a 6 over here living on the stack. Now I am going to say int star p, and I'm not going to give it a value yet. So what I've done is I've allocated memory on the stack for a pointer to an integer. And we're going to refer to that pointer with its name, which is p. Now what I'm going to do is I'm going to set up, oh, and I have this question mark over here because in C++, if you do not assign a value to something, the compiler does not give it a value of 0. It just uses whatever happens to be in memory there at the time. So if there was just cosmic space dust sitting in memory, then this value will be whatever that happens to be. So int star p, we don't know what value this is, and that's actually undefined. So we don't know what is actually there. So let's give it a value. Let's set up p so that it points to the address of I. So we can also point to things on the stack. We don't have to just point to things on the heap. So here, this ampersand, if we put ampersand before a variable name, then it means address of. So p, which is a pointer, is going to receive the address of I. So just type in the chat here, what will change, what will this question mark change to when I execute the next line of code? Can you figure that one out? Okay, so we had a couple of different answers. Most people said the correct answer of OX1. So why is that? Because what we've done is we've said, get us the address of variable I. And if you see up here, variable I lives at OX1. That's our memory address. So that's what gets inserted here. Now, So one other person said 6, which is kind of intuitive because it looks like we're assigning p the value of I, but this address of operator is the thing that gets in the way, right? So p is not getting the value of I, which would have been 6. It's getting the address of I. And our last line here, we're going to say star p equals 7. So if we have the star operator before a variable name here on its own, then this is the dereference operator. So this is quite confusing for new C++ programmers. Here we have a star, which is before a variable name, but it's in between a variable name and a type. So if you have type star name, then that is saying that this is a pointer to something. If you just have star variable name, then that's the dereference operator. So it's a little bit annoying, but that's all you can do. That's C++. And so what this says is essentially the dereference operator says, go to the place that p points to and set that value equal to what I want. Okay? So star p is going to be where this 6 is. Because what we do is we look up the value of p, which is 0x1. We dereference it, meaning we go to the location in memory, which is 0x1. So it's right here. Okay? That value is currently 6. And so when we execute this line of code, then the value of I is now 7. And do you see how this can get a little bit dangerous? Right? So it can get dangerous because nowhere in our code did we specifically modify the value of I. But at the end of the function, the value of I was changed. Okay? So you can pretty much do whatever you want with pointers. They can be very nasty. All right? You can point to any type of data, you can dereference it, and you can set values, and everyone at work will hate you if you do that. So just keep in mind that pointer use for this, one of the many reasons that using raw pointers is dangerous is because of stuff like this. Okay, let's look at another instance here. So we've got another program. I'm going to step through this really quickly. So we've got int array, so int star array. So this is a pointer to an integer. And some people like to say that in C and C++, pointers are arrays. That's not entirely true. Pointers just point to the beginning of an array. Okay? So if we said int star array equals new int 3, so what that says to the compiler is please go out and find me space on the heap for 3 integers. Okay? So what we do is the new operator finds the space for those 3 integers and stores a pointer to where it found that memory in ARR. So what we have at the end of executing that line is we have ARR on the stack, and that's 0x1, which is pointing to the beginning of that array. And so that array that we set up will occupy these 3 memory addresses. Now, that doesn't have any values yet, but if we say ARR0 equals 5, then what that will do is it will set this value equal to 5, right? Because it's the first element of the array. And then we're going to set ARR1 equal to 10. So 1 is the second element of the array. But why is 0 the first element and 1 the second element? Why did they do it that way? Well, here is the reason, if you've ever been wondering why arrays in good programming languages are 0 indexed instead of 1 indexed. Is because this ARR0, this syntax for looking up or storing things in an array, is essentially a shortcut way of saying this. So ARR0 means go to the address that ARR points to, skip ahead by 0 elements, and then look at that memory address. Okay? So this is the way you would do that if you want to do it manually, which is on this line of code. So if I want to set the third element, right, ARR2, then I can do this sort of manually by saying, go to where ARR is, so the memory address of ARR, which is right here at 0x1, add 2 to it, and then take that address and dereference it and set that equal to 20. So what that did is it looked over here at OX1, it added, so this is OX1, it added 2 to it to get OX3, it dereferenced it, so now we're in the value, and it set that value to 20, okay? So what this means is that ARRN, that syntax, is equal to dereferencing ARR plus N. And this next line is something absolutely hilarious that not a lot of people know, is that, look, this is just integer addition, this ARR and this N. So we can reverse this. And so we can have N plus ARR and dereference that. And so in C++, if you want to refer to the nth element of the array, you can say array n, or you can say n array. It's actually pretty hilarious. And don't ever do that in practice because it's just confusing, but it's something that's kind of funny. And ARR plus n is therefore equal to the address of ARRN. So these are all things that that let you use pointers in many different ways and be really confusing, but that's the mathematics behind pointers and arrays. This is, yeah. So if I wanted to put that array on the stack, I could do that as well. So let's look at the first thing here. So if I have a stack allocated array, then that would go into the stack right here. So similarly, we would have 3 elements reserved for that array. ARR0 equals 5, ARR1 equals 10, and ARR plus 2, dereference, is just ARR2, so that's equal to 20. So that's how you would do it on the stack. Okay, someone had a question, what happens if we dereference a variable that is not a pointer? That probably depends on the compiler or on the C++ specification, of which I am not sure. So it's going to do one of two things. It's going to be a compiler error, so it'll just be, it won't compile. I think that's probably the case. Or secondly, you're going to compile it and then run your program, dereference some value that is not a valid memory address, and you're going to get a segmentation fault. Okay? So it's 99 times out of 100, it's going to be one of those two things. 60% of the time, it works 100% of the time, right? Okay. So why are pointers a thing? Why would we ever want to use pointers? Well, there's several reasons why we would want to use pointers. First, and we'll talk about this a bit later, we must use pointers for inheritance, okay? So base star pointer equals new derived. If we have a base class and a derived class, we must use pointers or references, I'll get the references later, in order to do this. We may want to pass by value versus pass by reference. So modifying variables passed into a function, we would have to use pointers or references. Also, pointing to large data. So large data cannot live on the stack. If we want to store 100 megabytes of integers, we have to do that on the heap, and we're going to use pointers to do that. Okay, so I'm going to do a couple of more slides, and then we'll get to some... Actually, let's do some live programming now. Why not? So let's discard my annotations, and we will switch over to our programming. So we are going to go into a new program here, and we'll do some live programming, and we'll call this, I guess, pointers.cpp. So I am going to start writing this program. So I'm going to include IOStream so that I can look at, print some stuff out to the console. Then I'm going to have int main, and then we saw last time we have int argc char star argv. And then down here, we are going to return 0. All right, so that's our program. I have a macro set up to compile it. That is hopefully going to compile successfully. It did. All right. So what I'm going to do here is I'm going to have 2 integers. Let's say int a equals 10. So we're just going to show you that what I just taught you is real, right? I don't want you to just take my word for it. I want to show you in an implementation that it actually works, and then I want you to go out and try it later so that you can get used to pointers. So I'm going to have a value a, that's going to be stack allocated. Int b, let's call b 20, and so that's going to be heap allocated. So what I'm going to do now is I'm going to standard cout, that's the way I print stuff, and then I have a value of a, and then I'll print out a, and then a new line, and then I'm going to have value of b, and I'm going to print out b, and then a new line. So we're going to run this. Value of a is 10, value of b is 20. Okay, so that's pretty obvious. That's a pretty simple program. But now let's set up some pointers to stuff. Okay, so let's go int star pointer to a. I'll call it PA. And this is going to be the address of a. So that's how I would set up a pointer to a. Okay, is just get the address of a. Then I'm going to have the address or a pointer to b and have the address of b. So let me copy this, paste it down here, and instead of value of, I'm going to have pointer or address addr of a and addr of b. So this is going to be the value of PA, and this is going to be the value of PB. So see what we've done here? We're setting up two integers, we're printing their values, and now we are setting up pointers to those integers, and we are printing out the pointers, and that's going to be a memory address. So we've got the value of A as 10 and the value of B as 20. However, the address of A is this huge honkin' hexadecimal number, right? This is where that's actually physically living in RAM. And the address of B is another number. But you can see here that stack allocated memory, most of the time, if you declare it in a row on the stack, then the memory addresses are going to be separated by the size of that variable. So integers are 4 bytes. This address is just going to, this address is listed in bytes. And so we declared A on the stack, then we declared B on the stack. So let's look, is B 4 bytes later than A? It is. Okay, so that's pretty cool. We can actually show that A and B are stored contiguously in memory. However, let's look at why that could be dangerous. So let's pull this down again. Let's copy that, and now we're going to paste that down here. But watch this. I'm going to modify the value of B. Now, never ever do stuff like this. I'm just showing you why pointers can be so dangerous. Let's modify the value of B without ever referring to B itself. Okay? So, this is just for an exercise. We're not going to use this in our course. I'm just showing how pointers work and can be dangerous. So, how are we going to get at the value of B? Okay? Well, what we could do is we know that B comes 4 bytes after A. So let's see if we could do something. So let's get the address of B from the address of A. So this is going to be the address of A plus 1. Now the reason it's plus 1 is because the address of A is an integer, and we want to go 1 integer beyond that. And then if we dereference that to get the value and set it equal to 42, let's see what happens. Look at that. The value of B changed, but I never ever looked at B. I just know how the memory works, right? So I could go to the address of A, I know B comes next, so I can set the value of it. So this is why pointers are simultaneously ridiculously powerful, but ridiculously scary, right? Someone in the chat just said it's spooky. Yes, they are spooky. Okay. Let's look at another reason why you would want to use pointers. And we just, we did an example of that. But let's do something else. Okay, so we are going to set up our 2 pointers. So let's copy this again, and we're going to print out their values again after we do something. So let's make a function. And we are going to make a function, and that is going to be called, it's going to be a void function, so it's not going to return anything. And what we want to do is let's finify something, okay? So a fin is 5, right? So we're going to finify an input integer. So we're going to input a value I, we're going to make I equal to 5, and then that's it, right? So that's what the function does. Let me see if that works. Okay. So what we're going to do down here is I'm going to call finify on B. So what this should do is it should change B to be 5, right? Well, let's just look. Oh, it didn't. Value of A is 10. Value of B is 10. Value of A is 10 or 20. Value of A is 10. Value of B is 20. So why didn't that function modify the value of B? Well, let me go to the slides real quick and explain why that is. Okay, so I've got some slides here right before I come into that. All right. Okay. So it's this number 2 here, pass by value versus pass by reference. So let's have a look. What are C++ references? So references are essentially safer pointers. I shouldn't say safe pointers here. They are safe pointers. And how you set up a reference is instead of using an asterisk, you use the ampersand. Why in the name of God would they use the ampersand? It's used for the address of operator, but they did. Okay, so they just used the same symbol again. It's annoying. So the difference is, the reason why it's safe is that a reference must point to existing data. It can never just point to nothing. Okay, this makes them almost always safer. And so we are going to prefer using references to using pointers wherever possible in our code. Now, you should also, as fourth-year students, if you're in the course, be familiar with the concept of pass by value versus pass by reference. So by default, C++ passes all variables by value. So what that means is whenever you pass any variable into another function, it copies that variable into that function. If you then modify it in the function, you're just modifying the copy. You're not modifying the original version, okay? So we're going to see why this matters, but you may, so pass by value has, first, it's a cost for copying that possibly large amount of data. Also, you may want to modify the value that's passed. So what we can do is we could use pointers to accomplish pass by reference instead of pass by value, but ideally we would want to use references for that. So let's go back into our code and we are going to have a look at what I mean by that. So there's an example in the slides. Here we go. So why didn't this work then? Why didn't calling this function on B change its value to 5? Well, the reason was when we call this, C++ is passed by value. And so what it does is that I becomes a copy of B. And what we're doing is we're modifying the value of I, which is a copy, which in no way, shape, or form has anything to do with the original value of B. Okay? So how would I modify this to actually modify it, modify the value? Well, I could have the function take in a pointer to I. So remember, pointers are memory addresses. So then what I could do is I could say, okay, dereference I, go to the memory that I points to and change its value to I. Now, if I try to compile this, I'll get an error because B is not a pointer to an integer. It is a value. So I would have to pass in a pointer by saying pass in the address of B. So if I run this program now, you can see that it did in fact change that value. So if I want to be able to pass in something to a function and have that function modify the value of that thing, then I can use pointers for that. Okay? All right. References, however, are usually better and easier to use. So reference, as we just saw in the slide, if it's like a pointer, however, it's easier to use because we no longer have to dereference them. And we no longer have to use address of. So if I've specified that something takes in a reference to an integer, when I pass in an integer into that function, it no longer gets copied. A reference, or basically a pointer to that integer, is created and the value gets modified. So if I run this program using a reference, the value of b gets modified. So that's passed by reference. Okay, so passed by value, passed by reference. So there's a big difference. Okay, so let's go back to the slides for a second. Okay, so I've got an example in here for you, which is tenify instead of finify, and I've got those exact same things in there. Oh, I forgot to mention here that this function that I wrote, so if I have tenify int star a, when I dereference something, okay, if that address points to something that isn't valid, so if I do not control that memory address, if I don't have valid memory in there, then the pointer might be null or it might be invalid, and then what happens is I get a null pointer dereference, okay? And a null pointer dereference, or a bad pointer dereference, is going to cause a segmentation fault, which essentially crashes our program, okay? So in all of our functions, what we should do to be safe, okay, if we go back to our thing here, is wherever I'm using references, now we won't be doing this much this course, actually we might, is before I ever dereference a pointer, I'm going to check, I'm going to say if I is not equal to null pointer. Okay, that's what I would do there. Excuse me, I just need a drink. So the null pointer is just a pointer to the 0 address. Okay, let's go back into our slides. And this lecture may run a few minutes late just because I've had a bunch of questions and stuff. So pass by reference, we know that a reference will always be valid. Okay, so references will always be valid because they had to be passed in via a variable that exists somewhere. If we want to pass large data, then we're going to have to pass things by reference. Okay, so if I have like multiple megabytes or gigabytes of data that I want to pass into a function, again, C++ is passed by value, so it would copy this big variable, which is really bad. So I want to pass that in by a reference, and also, we saw before how when I pass something by a reference, the function can modify that something. If I don't want that data to be able to be modified, then I use a const reference, all right? So, pass by const reference. Whenever we pass a variable to a function via a reference that we don't want to be modified, use a const reference. Const is a keyword that declares that the variable cannot be modified inside the called function. And also, we only have to pass in the 8-byte reference and instead of passing in all the data if I went pass by value. So there are some exceptions to passing by reference, okay? You pretty much always want to pass primitive data types by value. So I said pass by const reference if possible, unless your data is a primitive data type or a data type which is under like 8 bytes in size. So I would not say int add const int reference a, const int reference b. I would just pass in the ints a and b. And the reason for this is just a performance thing. So if whenever you're using a reference, you are dereferencing it, looking it up in memory, and that dereferencing step is slower than just passing by value using primitives. So if that was confusing, don't really worry about it because it's just a bit of a performance hit. We are going to be passing shared pointers by value, but I haven't talked about shared pointers yet, so don't worry about that just yet. Okie doke. The next concept that we're going to talk about in C++ is called RAII. RAII stands for Resource Acquisition is Initialization. Bit of a weird name, but what RAII is, it's a software architecture paradigm in which if we use it properly, we almost no longer have to worry about managing our own memory or managing pointers. Okay, so it's really powerful. It's a really powerful software programming paradigm. RAII, in technical speak, binds the life cycle of a resource that must be acquired before use to the lifetime of an object. So what in the hell does that mean? We're going to show an example of that. But it's going to make life way easier by implementing things in a way that automatically manages memory and resources for us within an object. So, RAII implementation. What are we actually going to do? Essentially, wherever we have to use the heap, instead of calling new out in the wild and just throwing it around everywhere and then having to delete stuff, we're going to encapsulate our resources into a class. And that class constructor is going to acquire the resource and initialize it, and the destructor is going to release the resource. So the class itself should be instantiated such that it either has automatic storage duration or that storage is inside another RAII object. So what do I mean by that? I think it's going to be easier for me to explain this if I actually do a live coding example. So let's go back to the live coding and we're going to do this example. Okie doke. So here, all right. So dynamically sized arrays in, well, first of all, arrays in C and C++ are just like this. Int A 5. That will set up an array of size 5. But if I want like 10,000, I can no longer use the stack because the stack memory is so limited, okay? So what we have to do is we have to say int star A equals new int 10,000, okay? And that will set up, it will, like we said before, malloc will go be called and it will get us some contiguous memory of size 10,000 and return a pointer. Now, at some point, I'm going to have to free up that memory as well. So here, I'm going to do something with A, and at some point, I'm going to have to say delete the array A. And it's just it's a syntax for arrays, but essentially I'm going to have to call delete A at the appropriate time, and the rule is you're going to forget to do this somehow. And just as we saw previously in the slides, if we don't manually delete this array that was allocated on the heap, it's going to keep living there. And if we have a little function that's constantly allocating memory on the heap, that's where we get a memory leak. So our RAM usage just keeps going up and up and up, and that's a really, really bad thing. So if we wanted to use dynamically sized arrays in C++, what can we do in order to get around this? Well, I'll show you what we can do. We can use RAII. So, excuse me, man, talking a lot. So let's make a class, and we're going to call this class int array. So we're going to implement a class that is a wrapper around a raw integer array. And this will make it a lot easier for us, to actually use dynamically sized integer arrays in C++. And this class int array is going to mimic something like a vector. So if you've ever used a vector before, that's what this is going to look like. So what would we want to know about an int array? Well, maybe we would want to know, first of all, its size. Okay, so I'm going to store that size using a size t, and I'm going to give it an initial value of 0. And then I'm going to actually want the pointer to the heap memory where the array lives as well. So we're going to say int star array equals null pointer. So this is the initial value of that. Now I'm going to stick with my nomenclature here, and I'm going to say these are private member variables, and so they should be given the m underscore prefix. So my int array is going to have a size, and it's going to have the data, right? So now, those are private member variables. Let me show the public side of things. So I'm going to have a constructor called int array. And as a constructor argument to my array, int array class, I'm going to take in the desired size of the array, right? So this is going to be the size. So as we saw last time, we're going to use initializer lists for this. So m size is going to be the value, given the value of size. And I can also initialize the array down here via new int size. Okay, so that's using an initializer list to initialize a dynamically sized array. Let me confirm that this works. Okay, so that's the correct thing that happens. Now, by default, there's a default constructor for every class that we create. Okay, and that default constructor or destructor doesn't appear. You don't need to program it, right? So what's going to happen is that default destructor is going to, I can manually define it like this. So by default, it does nothing. Okay, so let's look at what's actually happening here. And I'm going to, inside here in my, standard cout int array constructor. And then in my, down here, I'm going to standard cout array destructor. Okay. The good thing about objects is when they go out of scope, the destructor is called. So here I'm going to say int array or arr, and then I'm going to pass in 100. So if I want to construct a new int array object, then I can say int array arr 100. So what's going to happen here? Well, I'll run the program. Okay, we see array constructor and array destructor. Why? Well, the array constructor is invoked here when I call this line of code. And then whenever I reach the end of the scope, my array is going to be, the class destructor is going to be called. Okay? So let's just review what we have going on here. When I construct this object, I'm setting the size of the object, and I'm initializing via the heap using the new keyword size for that array. And when I leave, when the scope is left for this function, the destructor gets called. So what I can do now is inside the destructor, I can say delete m underscore array. So all of the memory management is done for me inside this class, right? So what that means is that I can declare the dynamically sized array like this, and then when the end of the scope happens, the destructor is called, and the destructor of this object is going to do all the memory cleanup necessary for itself. So that's kind of the rule. That's what RAII does. What we've just done is we have implemented RAII. Okay? So RAII, resource acquisition is initialization. That's a bit of a weird way of saying it, but essentially our classes are going to clean up after themselves. That's what RAII is in a nutshell. So down here, we of course have to declare the initialization of our variable, but the destructor of the variable is going to handle everything else. All right. So let's just show you a cool thing here about C++ is if I want to, well, inside this int array, if I want to, actually, let me go back to the slides because I may have something here No, I want to continue on this for 1 second. So now that we've already made this int array class, let me show you something else about classes and operators, okay? So in Java, if you were making this class, how would you get access to this array? Well, maybe I'd use a get function, right? So maybe I have a set function and I have a get function. So void set is going to take in an index, and we're going to take in an int value. And what's going to happen? Well, I'm going to set the value of the array at that index equal to the value. So that's our setter function. And then we're going to have a get function, which takes in the index and then returns the array's value at that index. Okay? All right. So now what we can do is we can do something with our array. So we're going to say array.set. I want to set the value of index. Let's actually make this a little bit smaller. And what we're going to do up here is we're going to have a void print function. And this is going to say for size ti equals 0, I less than size I plus plus. Standard cout m array I new line. So what we just did here, I just made a function to print out everything in the array. So let's set 4 to 42 and then array.print. Let's see what happens. Okay, so here I have all 0 values except for 4. Let me actually print out the index as well. So I'm going to print out I and then a colon and then the value. So if I run it again, you can see that my array constructor was called. Then I set the value of array 4 equal to 42, and then I print it out. And then after the scope is resolved, my array destructor is called. Okay, now, what if we don't want to have to call get and set all the time? What if we want to use the same syntax as like a vector? Well, one other thing we can do in C++ are called operators. So I am going to have an operator which allows us to access the elements of the array using, or the elements of this class using the square bracket syntax. So what this is going to do is we're going to have a function or an operator which returns an integer reference, and I'll show you why that is in a second. That is going to be operator like this. So we're defining the square bracket operator, and the argument to the square bracket operator is the index that we want to get. And what this is going to do is it's going to return marray index. So now, down here, what we can do is we can say, instead of having to set things, we can say array 4 equals 55. Array 4 is going to call, or when I use the square bracket operator on the array variable, it passes in 4 as the parameter. It looks up that value in the array and returns a reference to it. So now ARR4 is a reference to that place in memory, and I can set that place in memory equal to 55. So let's look to see if that worked, and it did. So ARR4 equals 55 actually set the place in memory there. And the cool thing is, let's say if I print out, or if I say ARR3 equals 20, then down here I can also just print out ARR3. And that will print out 20. See? So it's cool. You can use operator overloading on your classes to do all sorts of cool stuff. And the thing is, you can't do that in Java. At least the last time I used Java, you cannot define the square bracket operator for vector. Therefore, you have to call get and set all the time, and it's really annoying. So that's just another cool thing about C++. Okie doke. So we're sort of almost done. Let me go back to the slides here. I know this is moving a little bit fast, but This is all a pre-recorded lecture that you can watch and skip through, and there'll be timestamps and stuff. So apologies for it being a bit fast. I'm just trying to give you like this speed run of C++, which is necessary for you to take the course. So that's what RAII is, and I've just made a couple of slides here that show you what RAII is. Okay, smart pointers in C++. Smart pointers are really going to be something that's going to make our quality of life a lot better in this course. So it can be really cumbersome to create our own RAII classes for every data type that we want to store a pointer to, right? So for example, if we wanted a pointer to a texture, well, we would have to create a texture pointer class if we wanted RAII. Right? If we wanted a pointer to an int, we would have an int pointer class. And you just saw me make an int array class. And so smart pointers smart pointers are a part of the C++ standard library. And there are different types of smart pointers which have very unique and niche uses. In this class, despite its slight performance hit, we are going to be using a shared pointer. And all a shared pointer, all you need to worry about, I'm not going to like do a whole lecture on the implementation of shared pointers, but you know how we just made that int array class, which is a wrapper around the memory handling for an integer array? Well, a smart pointer is going to be this wrapper around a pointer to an object, and it's going to handle all that RAII for us, okay? So a shared pointer is what's called a reference counted pointer. And what this means is you can pass it around by value to other functions and it won't destruct itself, and it will shared pointers operate identically to objects in Java. You can look at it that way, okay? Almost identically. So you can pass them around by value and the thing it points to will be modified. So reference counted pointers, they store an internal counter which is set to 1 in the constructor. Every time the shared pointer is copied, the counter increases by 1. Every time it destructs, the counter is decreased by 1. And then when the count reaches 0, the resource is deallocated. So it's really cool because we have this way of passing around data in a pretty efficient manner, not the most efficient, but pretty efficient in a way that handles the memory management for us. So here's how we would use that shared pointer. We declare, let's say we want to pass around a pointer to my class object. So I have this my class object here. Instead of saying my class star p equals new my class, we can say, okay, I'm going to create a shared pointer to my class. The variable name is going to be called p, and the pointer that initializes it is going to be a new my class. Now, I know that this is the wrong way to do it. I'm going to have the right way to do it in the next slide. Now I can pass around that pointer, or that shared pointer, by value into other functions. So when I set this up, the internal reference count of that pointer is equal to 1. Maybe I pass it into this function. Then the reference counter is going to be 2 because we've copied the object. We're going to do something with that data. Then when it destructs, the reference count is now 1. Then I do something else, and then we're going to deallocate it, and it's 0. So I don't even know why I included this slide because it's a little bit confusing. But essentially, shared pointers are going to make our life pretty easy in this course. And the correct way that you want to initialize a shared pointer is via standard make shared. So if I want a pointer to a my class object, I will say auto, because auto is great, auto p equals standard make shared my class with the arguments. Okay, so that is shared pointers. That is how we will be using them in this course, and they will be very intuitive once we start getting into it. All right. Inheritance. Inheritance is also something that you should be familiar with. How is that handled in C++? Well, it's basically the same thing as Java or in other programming languages that have polymorphism. Member variable types. Public member variables in a base class are seen by all of the derived classes. Private variables are seen by none, and protected are only seen by derived. So public member variables, everyone can see them. In private, only that class, the base class, can see them. And protected member variables can only be seen by derived classes. So what you do is you would say, in order to use inheritance, you has class derived equals public base, just like you would have in Java. It's very close to the same syntax. So 99% of the time, we're just going to be using public base class in order to do this. And this is just, excuse me, my throat's getting a bit dry. One sec. So this is just one slide that says inheritance in C++ is very similar to the syntax you said before. And here's how variables are the visibility of variables works in C++. And what's the saying? There's a really funny saying. Let me try and remember it. So your derived classes can see protected or public things, but not private things. And so there's a way in C++ to allow certain classes to see private variables via the friend keyword. And so the saying is, in C++, friends can see your privates, but your children can't. Okay, so that's what I was trying to... I ruined that joke by taking too long, but it's a funny saying. Okay. So, with all that being said, what in the hell was the point of the last hour and 20 minutes? It was setting up how we are going to allocate and pass data for the rest of the course, because how we manage our memory is very important for game programming. So if possible, first, use the stack. So for small local variables, we're going to use the stack. And whenever we pass variables to functions, the rule is if the size of the data of that variable is greater than 8 bytes, pass it by a const reference. Otherwise, just pass the data by value. The next rule, if you need to use heap memory, use a smart pointer. So use a shared pointer in this course. Also, if you are setting up an inheritance, you can use shared pointers for inheritance as well. So I can say standard shared pointer of the base class is equal to standard make shared of a derived class. So if I have, I don't know, like a component base class and some derived specific components, I can say standard shared pointer component equals new make shared transform component, and we'll see that. Only when absolutely necessary will you ever use raw pointers, so the asterisks or the new keyword. And this whole course, we will go the whole course without using, hopefully, any new keywords or raw pointers. Okay. The last thing I want to talk about in this lecture is templates. Templates are extremely powerful, but they can also be extremely complicated. You can go down a very, very deep rabbit hole with templates, and we are just looking at that hole in this course. We're not going down it. We're going to keep it very, very simple. And what we can use templates for is for generics, okay? So what we're going to do is let's just do a little coding example of C++ templates to the thing that we've already showed. So that's it for the slides. I'm going to go back to one last coding example and show how useful templates can actually be. All right? So let's go back here and we'll go back to our programming. So here in our code, what we did was we made an int array class. And as you can see, the int array class stores an array of integers, right? And so what would we do if we wanted to store an array of doubles or an array of floats, right? That's a problem now because we've hard-coded this class to only store integers. And so what we can do is we can use generics. And generics will allow us to store whatever we want in this class. So template class T, and instead of int array, we're going to call this dynamic array. And so to make something generic and store whatever we want, so we could have one array class that stored multiple types, the first thing we do is we declare that this class is going to be templated. And the class type is going to be this variable, and we're just keeping it simple. We're just going to call it T. Some people use underscore T or type or whatever. We're just going to use T. And now what we're going to do is anywhere that in the code for this class that we used to refer to an integer, we're now going to refer to T. Oh, excuse me. So instead of int, we're going to have an array of type T's. Down here, instead of int array, that's going to now be just called dynamic array. Instead of a new int, this is a new T, and the destructor is going to be a dynamic array destructor. This is fine, it destructs the array. So here the getter function was returning an int, but now it's going to return a T instead. Here, setting was setting an int value. Now we're going to set a T value instead. And down here, print should still work for us. The last thing is this square bracket operator. So instead of returning a reference to an int, we're going to return a reference to a T. And now what we do down here is we now have a dynamic array. And in order to specify the type of the array, we are going to put in brackets a type, and then that int or float or double, whatever we put in here, is going to be the T that's used up at the top. And the way that this works, it's a preprocessor directive. So if I say dynamic array int and dynamic array float, what the preprocessor will do is actually create in the code two copies of this dynamic array class, one of them that stores ints and one of them that stores floats. So it just saves us a lot of typing. Okay, so let's compile this, and there we go. So now this is a dynamic array double that I can store like arbitrary double floating point stuff in. See how that works? So now I can store dynamic array my class if I want to, right? So this is how templates work, and this is how we're going to use them in the course. So we're going to be able to create a single class, or a single data container that is capable of storing multiple types of things based on how we want it to act. All right, and that is as deep as we're going to go with templates, is just to implement very, very basic generics. Cool. So let's go back to the course schedule, because I know it went a little bit long, maybe 15 minutes over time today. Sorry about that. Had lots of really good questions and some cool coding examples with all of my mistakes in them. So on Tuesday, we're going to be going over assignment 1. So in the next lecture, we're going over assignment 1, and we're also going over SFML. So SFML is the graphics library that we're going to be using. And I'll also be talking about Visual Studio. So Visual Studio is the way you're going to be doing this course in Windows for this course. You can use Visual Studio Code or whatever, Xcode or something on Mac. It doesn't matter what you use, but I highly recommend using Visual Studio because I'm releasing Visual Studio projects for all the assignments. So please tune in to the next lecture. It's really important. We're going to be talking about like the base functionality for all of our assignments going forward in the course. And I think those assignments are going to be really fun. So thanks, and I'll see you in the next lecture.